welcome to today's webinar with the title Basics of Printed Circuit Board Production Part 2, Flex and RIGID.flex. I'm Andreas Scherr, your host of today's RIGID Electronic Circuit Board Technology webinar, and would like to welcome you. The speaker of today's webinar is our expert in RIGID.flex, Guido Birnat, from our Technical Project Management at RIGID Electronic Circuit Board Technology. Welcome, Guido.
I would also like to welcome you to our webinar, Basic, Flexible and Rigid Flexible Printed Circuit Boards. This webinar is intended as an introduction to flex and rigid flex technologies. Before we begin, I would like to shortly introduce myself. My name is Guido Birnat, and I have been working in the PCB industry for about 30 years now. Since September 2020, I'm supporting the technical product management at RIGID Electronic Circuit Printed Boards Technology. This webinar will focus on two stack-ups, one FXRI and two FXRI flex variants, which are also called asymmetric stack-ups. You will also learn a compilation of the standard base materials required. Furthermore, I will present the production process of a rigid flex printed circuit board. A short introduction over flexible and rigid flexible PCBs. 3D installation for optimal utilizations and limited installation volume available. The flexible area can be bent with very small bending radii. High integration density, high integration density and neutralization is possible. Very robust and high reliability because a lot of soldering points and plug connections can be omitted. The total connection of the application can be realized by one single flex or rigid flex PCB. Small weight and space requirements. Uniform reproducible electrical properties, for example, impedance, crosstalks, and signal integrity. Please, sorry. Ich bekomme dauernd eine Error-Meldung hier vorne bei mir. Sorry. Okay. I will start with the features from FPC boards, or the flexible printed circuit boards. Flexible printed circuit boards are essentially made of flexible base materials. One layered design up to high layered flex multilayers with buried vias and blind vias are possible. For RIGID Electronic, the maximum layer count is 8 layers for the flex technologies. High integration density and miniaturizations. Partial stiffeners at different areas with different thicknesses on the top and the bottom side are possible. The partial stiffeners are not electrical connected to the flex layer. It's a very important message. No through plating with the flex layer to the rigid stiffeners. Small weight and space requirements, uniform reproducible electrical properties. The features for the rigid flex boards, called the same, rigid flex PCBs consist of rigid flex and flexible areas. The rigid multilayered areas are connected by flexible base material and include through plate connections. Rigid flex PCBs are made of at least 2 copper layers. The third de-installation for optimization utilizations of the limited installation volume available. The flexible area can be bent with very small bending radii. High integration and density and miniaturizations. The total connection of a product can be realized with one RIGID.flex board, small weight and space requirements, and uniform reproducible electrical properties, impedance crosstalks, and signal integrity. And now a summary of the characteristics from flex and RIGID.flex boards. Flexible PCBs, FPCs, have no electric connection with functional stiffeners, rigid areas. RIGID.flex PCBs consist of rigid and flexible areas and include vias. RIGID.flex PCBs have at least two copper layers. It's very important. Flex and flex rigid technology are used in all markets: industry, medicine, aerospace, telecommunication, automotive, and also in the consumer electronics. The motivation for using flex, our RIGID.flex technology, are miniaturizations, dynamic movements, reliability, signal integrity, as well as system advantage and price. And now I have one question for you. What is the main difference between flexible and rigid flexible printed circuit boards? And Andreas, please start the questions.
So now you should see the blue screen where you can make a choice and decide for one of the 5 possibilities. So I can see there are different decisions. It's not just one or the correct answer. We've got 30% participation already. I will wait another 10 seconds roundabout. Then I will close the poll and show the result. So we have passed 60%. That's good. Another 2 or 3 seconds. So that's it. And I'll close the poll and show you the result. So we have 2 top answers. The first one, they are made of different materials, 30% and 34% flexible PCBs have no rigid areas. So the correct one would be electrical connection between rigid and flexible material. So 21% of you are correct. And with that, I fade out and give back to Guido.
Okay. I think the answer is clear. The right answer was the rigid materials are electrically connected to the flexible materials. For example, the wrong one answer, flex printed circuit boards have no rigid areas. It is possible you use stiffeners in areas from the flex print, for example. So, okay. And now the standard base material for the technology flex and RIGID.flex printed circuit boards. Standard rigid PCB are made of 3 basic materials: Prevec, copper foil, and the core material FR4. These materials are, of course, also used in the flex rigid technology. To begin, I describe the flexible base materials with copper. Flexible base materials are ever in some variation. Only the standard material are shown here. These materials are used 98% of good electronic. The copper thickness from the base material are standard 35 microns, and 70 microns is also possible. 1 or double side material. The core thickness from the polyamide core gives in different variation, 25 microns, 50 microns, 75 microns, and 100 microns. This kind of thickness are standard for wind electronic. Glue and adhesive base materials is also possible. The wind electronic use only adhesiveless materials. Our standard suppliers are Panasonic and also DuPont. The material called Pyralux AP from DuPont or from Panasonic is R770 or Panasonic R775. This base material is one polyamide core in the middle of the core and double-side copper. And now is the flexible composite and protective materials. In the flex and RIGID.flex technology, a variety of so-called composite materials is used. Cover layer or cover foil. Hereby, the cover areas are signals as protect. These materials will be applied with thermal process pressing. The cover layer is a composite material. This material consists of two materials. In this case, the polyamide and the adhesive layer. The standard thickness here are 25 microns or 50 microns polyamide with a layer of acryl or epoxy adhesive. The common adhesive thickness here are also 25 or 50 microns. The next one is a bond ply or composite foil. With this material, the flexible and rigid materials are glued together. Here to the thermal process of pressing is used. The bond ply, like the cover layer, is a composite material consisting of polyamide core with an adhesive layer on both sides. Here too, the adhesive layer consists of acryl or epoxy adhesive. The next one is the adhesive or the glue, consists only of an epoxy or acryl adhesive layer. The standard thickness here are 25, 50, 75, and 100 micron. The standard suppliers from these materials are DuPont, Germany. And now the rigid composite and base materials FR4 and pre-wax. These base and composite materials are the classic materials for all technologies in the PCB industry. The pre-wax, standard pre-wax, the called pre-wax is the adhesive medium for all common PCB technologies. With pre-wax, the single rigid and flexible cores, inner layers or copper foils will be plugged or bonded. This bonding is done only the thermal process pressing. The pre-wax consists of a glass fabric textile which is pre-impregnated with the resin and hardeners. The TG values area for by word is standard TG 135, TG 150, and TG 170. The classic RIGID.flex pre-wax, this is called pre-wax low flow, consists of glass pre-wax, the same with the standard pre-wax textile, which is pre-impregnated with the resin and hardeners. The difference to the normal pre-wax lies in the recipe of resin and hardeners. Common thickness are the 106. The types are 106 or 1018. The TG values are standard TG 135 and 115. The rigid composite and base materials FR4. FR4 describes a class of flame retardant composite materials. The composite materials FR4 has been used in the PCB technology since 1968 and is absolute the standard. The standard copper thickness are 18 or 35 microns copper thickness. 17 microns copper thickness is also possible for the standard technology. The core thickness are very variation from 50, 60, 100 and so on, big up to 1200 microns. Our standard TG values are the same for the playback. You can see. And now I will show you it comes 4 flex stack-ups. All the previously listed materials are used here. FR4 core, this is start. The FR4 core, the flex core, glues, and a new material, the flexible solder mask. 1 and 2 layer stack-ups we call pure flex. You can see we have the flexible core material, base material, polyamide core is 50 microns. We have a stiffener, partial stiffener. We have a layer glue, and the new one is the flexible solder mask. The next one is the double side flex print. We have the same materials. We have the polyamide core, double side copper. We have through holes. We have partial stiffener on both sides. Flexible solder mask. 1 and 2 flex prints we call pure flex. The next stack-up is a 4-layer flex print. 3 to 8 layers stack-ups we call slim flex. Pure flex 1, 2 flex prints. 3 up to 8 layers are the technology called slim flex. The slim flex technology allows used to use a high HDI technology. Partial stiffness is possible. The same with pure flex technology. You see 3 polyamide cores. You see 3 polyamide cores, 2 adhesive epoxy sheets, flexible solder mask, and through holes. For the next stack-up, you can see that the 4F high slim flex HDI also possible. We have the same materials, but we have from the top side and from the bottom side micro vias. We have burial wires, inner layer core, and we have through holes, and also we have stacked vias from top to the inner layer. Now I would like to present you for example of standard rigid flex stack-ups. The first one called standard 1F XRI stack-up. For example, the syntax. The 1F is the layer print, so counts the layer, flex layer print, and the X is the count from the rigid layers. For this example, we have a 1F 3RI stack-up. You see 1 polyamide core. We have 1 core with low flow prepreg. We have a standard FR4 core, and on the bottom side we have 2 standard prepregs. On the top, the low flow prepreg, and on the bottom, the standard prepreg, and the copper foil. The next example from StuckUp is the standard 2F-XRI example. This is one flex layer on the top, outside top, and one flex layer on the inner layer too. For example, the syntax we call 2F 2RI StuckUp. And we have two rigid layers, bottom and the inner layer. Please wait. You can see the polyamide core. In this case, we have two low flow prevex sheets. We have one FR4 core, one standard prevex, and one copper foil. Through holes. And the cover from the signals are on the top side with flexible solder mask, and for the inner layer L2 we use a cover layer, partial cover layer. You see the cover layer is not complete, this is partial in the flex area. The next example is a 1F5 RI HDI StuckUp. The stationary is 1 for B1. It's called one from top side to inner layer 2 microvias, from the bottom side microvias to inner layer 5. We also have buried vias from layer 2 to layer 5. It's classic standard HDI design for this rigid flex. The next one is a standard 2F 2RI with microvias. I will show you this absolute standard to use double-side microvias technology for the 2F StuckUp. Now the summary base material in StuckUps. All common flexible base materials can be used here. With electronic, using the material of DuPont and Panasonic. Also, all common rigid base materials can be used here. By with electronic, the materials we are using the materials from Isola, Technodam Nanya, Panasonic, and Showa Hitachi. Standard TG values are 135, 150, and 170. Important information for you is that all StuckUps from Flex and rigid flex are always a mix of different base and composite materials, and therefore hybrids. Now I would like to show you a manufacturing process from the rigid flex circuit board. Due to time constraints, I can only show you a highly summarized presentation. As an example, I have chosen a 1F7RI rigid flex StuckUp. One flex layer and 7 rigid layer. On the left side, you see the cross section from the PCB, and on the right side, a top view of our production panel. The contour and placement in the production panel of the PCB is shown schematically here. 5 PCBs, rigid area, flex area, rigid area. First of all, we want to produce the inner layers. The starting materials for the FR cores laminated on both sides with copper. Plus FR4 core, FR4 core. The FR4 base material now runs a process sequence cleaning, laminating, resist, exposure, developing, etching, and stripping. And the PCB layout is now visible in the copper structure. This is a FF4 core with your layout. Now we come to the special feature of the RIGID.flex technologies. Certain base and composite materials have to be mechanically processed. The processes are not needed for the production of rigid PCB. The FF4 core of layer 2 and layer 3 is mechanically scored or grooved. It's a transition from rigid to flex. This and this. You can see the detail. You can see the score with the milling tool or groove with the milling tool. On the core, only the core L2, L3. The core up to the flex layer. The next special feature is the milling process for the low flow prereq to the flex layer. With the milling process, we reduce partial the low flow prereq in the flex area. Then the next process is all materials are laminated with the thermal process pressing. This process takes place under vacuum pressure and temperature up to approx 200 degrees. After the pressing process, you can see the cross section of the press production panel. Also, you can see the unbonded flex area. For example, polyamide core, low flow prereq, FF4 core, standard prereq, FF4 core, standard prereq, FF4 core, standard prereq, copper foil. Always eliminated, and in this area, flex area, is an unbonded flex area. The next process are now drilling, the galvanic process, exposure process, etching, outer layers, and the flex solder mask and standard solder mask, and the surface finish, for example, chemical gold, and now the electrical test. The next process is the contour milling process. However, before the outer contour can be finished, the flex area must also be partially machined beforehand. This process is called depth milling. Now you can see the final RIGID.flex PCB. After then, the PCB will be cleaned, visually inspected, and shipped. Now you can assemble your PCB. And now an application example for RIGID.flex PCB. This PCB has gone through the same processes as just presented. On the picture, you can see a torque tool. The stacker for this torque tool was a 1F3II stack up. The polyimide core thickness was 15 microns. The material was FF4 with TG150. In the flex area, we used not the cover layer, we used flex solder mask. The motivation was the integration of all electronics and the displays and keyboard and the energy storage into the hand to be integrated. So here you can see the storage, all the rigid flex areas and the rigid areas. The motivation was miniaturizations, variability, and system advantage at once. Now we have learned that the production of a rigid flex circuit board is fundamentally different from a standard rigid circuit board. Especially, the use of flexible materials and their mechanical processing requires elementary design rules. I would like to draw your attention for two design rules, the point G, D and G. The design rules are very important for the rigid flex transition. For more information, please use our website, and you can see the two design rules for the technology 1F XRI and 2F XRI. Finally, I would like to draw your attention for the next webinar in the series PCB Production RIGID.flex Part 3. In this webinar, we will talk more about the possible option of the RIGID.flex technology. In this webinar, we will again show standard stack-ups. The standard stack-up called XRI, 2F XRI. The syntax is, for example, 3 rigid layers, 2 flex layers, 3 rigid layers. In this webinar, we will again show the technology from the standard stack-ups and also the non-standard stack-ups. This time we will talk about symmetrical stack-ups construction. This kind of stack-ups called symmetrical stack-ups. This means that the flex layers are located inside of the PCB. Yeah, thank you very much for your attention.